Hello everyone, so this is lecture 2 and lecture 3 combined together in this video. And in this video lecture, we will discuss the RF spectrum, some modern RF systems. We will talk about electrical signals. We will study their attributes and their features. We will introduce you the concept of Fourier series. And we'll give you some historical context of Fourier series. We'll talk about Fourier transforms as well, but we'll focus more on Fourier series. And then we will move into the time domain representation of signals, and certainly the one that is more important, the frequency domain representation of the signal. So this is a heavy 2-lecture combined together. The objective why I decided to combine the lectures together is that I wanted to keep a continuity to the lectures, and that's why I thought it would be important that they remain together. This doesn't mean that you should sit in one setting and look at the entire roughly 2 hours and 45, 2 hour and 50 minutes video altogether. You could break it into different slices and then study topic after topic gradually throughout the week and throughout the days. So you could do that on your own time. I will put an outline of the lecture just below the video on YouTube, so you'll be able to jump from topic to topic, and I hope that's going to be helpful for you. That's about it. I hope you enjoy the lecture, and let's get going. As we begin lecture 2, the objective that we will follow would be essentially to continue where we left it in lecture 1. At the end of lecture 1, we talked about a block diagram for a communication system. And so here I'm going to show you the block diagram again, and then we'll try to kind of understand how does one go about designing a communication system. Designing a communication system is a vast area. There are so many angles and perspectives that one can take in designing a communication system, although we're still in the physical, the Mac layer. But the one big perspective or one big approach in designing a communication system is really based on viewpoints, and that's the objective of this slide. So let's recap what we did. So where we left it in the last lecture, we saw that when we transmit, there's always some input signal, some signal that we have, some information that we're trying to convey. So this is the information. It's a signal. For instance, it could be voice, it could be computer data, it could be video, etc. And this information, this signal that we have, we modulate the signal. We send it into a box, a transmitter. It gets modulated, and then it goes into the channel, the medium of the communication, and at the end we receive the signal by using some device, some receiver device, and we get, of course, the output signal. The goal, of course, is to have this output signal to look more or less like the input signal, but as we said before, this will never be the case. So that's where we left it last time. So now the question that we ask in today's lecture is the following. How do we design the transmitter and receiver? In other words, what is the transmitter and receiver? How do we put it? How do we decide what should the transmitter do? What should the receiver do? In other words, how do we kind of determine how the modulation should be? We said modulation, in its most basic explanation, is just a way of modifying the signal so that the signal can go from here to the channel, so that the signal can be traveled. And one of the big kind of ideas that we do, or some of the biggest elements that are done by the modulator, is essentially up conversion. So you up convert, you transmit your signal at a higher frequency. So now the legitimate question is to ask is, how do we design this device? How do we design this other device, this receiver? So that's the question that we ask. The answer could be as follows. And I wrote it to you here so we could read it together. To design the communication system, i.e. the transmitter and the receiver, or if you want, if we don't want to say transmitter and receiver, we could also say the modulator and the demodulator, or sometimes we have a device that can transmit and receive. So now we would be talking of a modem. And perhaps I should mention these terminologies because I assume you might have heard them, but perhaps the meaning behind them is not very clear. So in communication systems, some devices will have the capacity to transmit, but not to receive. Some devices will have the capacity to receive, but not transmit. And some devices will have the capacity to transmit and to receive. So in this picture, this device here that you see is only a transmitter. It can only transmit, but it cannot receive. This device here, it can only receive, but it cannot transmit. Once you have a device that can transmit and receive, it has a name, and the name that typically people use in our field is transceiver. In a transceiver, within a transceiver, you have essentially another term that you know, or that you have heard, a modem. A modem basically is made of two words. Mode, which comes from modulator, and dum, which comes from a demodulator. So it's just two words put together, and that's your modem. So essentially, it's anytime you hear the word modem, it's just a communication device that gives you the capacity to transmit and to receive. In other words, it's a transceiver device. So you could think of, for instance, your laptop machine. You have a laptop machine, and your laptop is connected to a Wi-Fi communication. Wi-Fi that you're connected to, let's say you're at home, you're probably connected to a modem, a wireless modem. And so you are able to transmit to that modem, and you're able to receive signal from the modem. You're able to transmit a signal to the modem. Say, for instance, you're writing an email and you're attaching an attachment. Anytime you're sending something to the internet, that's transmitting. You can think of it that way. Anytime you're downloading something from the internet, say you're watching a movie on Netflix, you're downloading that this is receiving a signal. It's just one way of looking at transmitting and receiving. And so your laptop essentially has a modem. You're able to transmit and receive. And the device, this access point that you have at home, this router, if you want, is essentially also a modem. It enables you to transmit and to receive. It's a transceiver device. So there's just some terminologies that perhaps could be useful, and I just wanted to mention it to you. So now what we have here is the following. Let's just read it again because I kind of got distracted with some terminologies. To design the communication system, in other words, to design the transmitter and to design the receiver, it is necessary to understand the related channel. So anytime you are stranded to figure out what to put in your transmitter, how to build this device and how to build this device, you always have to ask yourself, what is the channel, right? What is the channel? It's very important to understand and to predict somehow the channel. Now, the channel is a very complicated medium, right? It's very hard to sometimes understand your channel with very high precision. You have various elements that could deteriorate your signal. You have noise, you have fading, you have interference, and many of these factors are actually random, right? So they are elements that will deteriorate the quality of your signal, but they are random. It's very hard to kind of know how it behaves because it's a random process. It's a random behavior. So quite often you might get something like this. So this is some random behavior of the channel, right? So you have the receive power and you have the distance between transmitter and receiver, and this is, let's say, the way it behaves. So that's one approach to understand the channel, to kind of get a sense of how the channel is, what happens to it when information is being sent between transmitter and receiver. Okay, so this picture is really related to this, to the channel. Now, here in here, if you notice, I said it is very important to understand or predict somehow the channel. Now, how do you predict the channel if it's random? Well, there are different tools. There are different statistical tools that enable us to predict the channel sometimes, right? So, for instance, I could show you a picture here. This is also the channel, and in it, what we have is we are able to detect the behavior of the channel. Now, once you are able to somehow predict it analytically, we're using some statistical tools, then that's something that you could use to design your transmitter and receiver. Right? It enables you to design your transmitter and receiver. Now, let's go see some varieties of different modulation schemes that you could use. And in fact, perhaps I mentioned it in lecture 1, when you design or when you use a transmitter and a receiver, you have the option, right? So you have the option to either use analog modulation or digital modulation, right? So by default, today, in 2020 onward, and for all these past years, it is very conventional that one would always opt for digital communication. It has a lot of features that makes the communication more reliable. The signal will have less deterioration in the channel. It is more secure. It uses such tools as error correcting codes. Error correcting codes does not exist in analog communication. So that kind of helps in making the channel better. It gives better coverage and so on and so forth. So digital communication is fine. But there is also the option of going ahead with analog modulation. And like we said, the first part of the course is analog modulation. The second part of the course is digital modulation. So what are the different options that you have here? Well, one option would be for these boxes, this one here and this one here, is to use, say, AM. AM, kind of what you have on the radio, this device that sometimes you turn on, your typical analog radio that you have, perhaps the radio that you have in the car. This device is an analog technology. It's an AM. AM stands for amplitude modulation, and essentially you would have an AM modulator here, and you would have an AM demodulator here. This is one option. So this is one possibility. Another possibility is, for instance, to use FM. You would have frequency modulator here, and you would have the reverse function here, a frequency demodulator. There is also another option is to use, for instance, PM, phase modulation. You would have a phase modulation, a PM modulator here, and a PM demodulator here. There's also the option of PWM, pulse width modulation, so this is also a possibility. These are all different varieties of analog modulations. Now, what do they each mean? Well, we'll talk about that. We'll talk about them in the upcoming lectures. So in reality, what we will cover is really AM and FM. We don't really have time to cover PWM in phase modulation. We will cover AM modulation and frequency modulation in depth. So we'll have perhaps a lecture and a half on this one, perhaps a lecture on this one, but not beyond that. But for the others, we won't. There are other possibilities. You could look them up. Pulse width modulation is in fact a quite famous modulation technique. It's a baseband modulation technique. Essentially, it has various applications. Some applications in telecommunications in our field, some applications for voltage regulation, some applications in ADC, so analog to digital communications. You enter an analog signal into a pulse width modulation, and you get a digital signal from the output from a pulse width modulation. Right? So you enter something analog. This is your PWM, pulse width modulation. In here, what you get is a digital signal. So that's one approach to use PWM for an ADC, analog to digital converter. I perhaps assume that you guys have seen this somewhere else. So essentially what it does is that the information is encoded in the width of a pulse, the width of a binary pulse. So you have a pulse that's 0 and 1, or if you want 0 volt and 5 volts, or 0 volts and 3.3 volts, and within the pulse of a 3.3 volt, that's where the information is, right? That's the value of the amplitude of your analog signal that is encoded. So that's one approach. FM, the information is encoded in the phase. PM, the information is encoded in the phase. FM, the information is encoded in the frequency, and AM, the information is encoded in the amplitude. Now, perhaps they all sound like very technical. Don't worry, we will cover them in future lectures in depth, so you'll understand what these terminologies are. In the second part of the course, you'll cover such things as ASK, so amplitude shift keying, FSK, frequency shift keying, PSK, phase shift keying, IQ, in-phase quadrature modulation, or if you will, QAM, quadrature amplitude modulation. These are all things that that are very practical and that are used in our modern technologies, from your Wi-Fi to your Zigbee to your Bluetooth to your 4G LTE to your 5G communications to your V2X communications. All these different varieties of technologies that we have today, they use some, in fact, these different modulation schemes. So let's say if you use, I don't know, let's pick one, an ASK modulation, an amplitude shift keying, you will have an ASK modulator here, and you will have an ASK demodulator here, right? So these are different varieties of modulation. So now that we saw how one would approach designing a communication, the message that I want you to carry from this slide is that when you decide what to put in this box or in this one, and in fact, whatever you put here should do the functionality of the receiver will essentially be the reverse of the transmitter, right? So whatever you put here you would put the reverse of it. If you put an AM modulator, you put an AM demodulator. So I hope that's clear. But whatever you decide to put here, irrespective of the modulation, you need to always ask yourself, what is the channel? The channel tells you which one to pick. So you have a menu of option, and then based on the channel that you have, you pick the one that makes sense. Okay, and the application. So the channel and the application. And so that's how designing a communication is. Not all modulation schemes make sense for all type of application. Say you have satellite communication, you will use one type of modulation scheme as opposed to, let's say, LTE, 4G LTE, or 5G communication, or narrowband IoT. You'll have a different type of modulation scheme. So the application and the channel, type of channel that you consider, makes you decide the type of a modulation scheme to use. So that's kind of the big idea that I want you to perhaps get from this slide. There are a few other things that I wanted to mention as well. Now, as we said, this is the first part of the course. This is the second part of the course. These are referred to as analog communication schemes. The following are referred to as digital communication schemes. Few other things that we should mention. The input signal. The input signal, in reality, it could be both, right? It could be analog, like inherently from its first state, it could be an analog signal, let's say your voice, or it could be in fact a digital signal. So this is not necessarily always analog. It could also be digital. So it depends on different scenarios. So if it is digital and you are using if your input signal is a digital signal, then what we would assume is that you are considering essentially some digital modulation scheme. If you are using an analog signal rather, then you are essentially using an analog modulation scheme. So let's say you put some analog signal here. Let's say you put your voice, and what you get in the output would also be analog, right? So it will still be analog. The only difference is that it operates at a higher frequency, and the modulator would, let's say, be AM. If you are putting a digital signal, so a bunch of a sequence of zeros in one, the modulator would then modify your signal, and what you transmit is the signal here is in fact analog. So you are using a digital modulator. Your input signal is digital, but the output is analog. So that's one possibility. Sometimes your input is also analog, let's say a voice, but you want to use a digital transmitter. You want to use a digital modulation. So what you do before you pass it into this, you pass it through some ADC, an analog to digital converter, and then after it goes into an ADC, then you could let it go into a your digital modulator. And then what you get here would be an analog. So there's different varieties of how this is approached, right? So it could get you could gradually complicate the system, but there's just some things to keep an idea of. This could be messy. I do recognize that, but I think you'll get a better understanding as we move along the course and as you do the problems in the exam. That should help. So now let's just move on to the next slide. In this slide, I'm interested to show you some of the communication systems that we have in real life. We have many communication systems in real life, as you could attest. There's so many different applications that exist. So it's really hard to have all of them. I try to include as many as possible, and I'd like to show it to you here in this slide. So the slide may, at the end, it will be a bit too intense, but we'll build it together so that you'll follow along. So the first one, again, we always go back to the block diagram, and I think that should essentially kind of makes us grounded to the whole concept of communications. Input signal, transmitter, channel, receiver, output signal. So the question is, when you have different applications, you will essentially have applications that are there because the channel will vary from one type to another, and we'll see some of them. So if you look at the channel, one possibility for the channel is that it be in a wireline communication. So you have some in other words, the propagation for your communication is guided. Another possibility for your channel is that it simply be left, your signal is just transmitted in the air. So it has the common terminology, which is wireless communications. Or free propagation. It's just up in the air, and then the signal, hopefully, you're hoping that the signal is detected at the receiver. So if you right away compare both of them between wireline communication and wireless communications, right off the bat, you should immediately identify that wireless communications is always at a lesser quality. The quality of the communication will be less with wireless communications. And the key reason for that is that the propagation is not guided. It could go anywhere, and that's the key reason. But it has the key advantage of being, it gives us more freedom, right? We're not bounded to some cord. We could move freely and at the same time have connectivity. So there are pros and cons with wireless communications, and there are pros and cons with wireline communications. I think it is very hard to assume that because wireline communication is more reliable, that all applications should be wireline. And it is very hard to assume that because wireless communications is more flexible, that all communication should be wireless. In reality, in real life, you will have applications where wireline makes total sense, and you will have applications where wireless communications makes total sense because of flexibility. And here, wireline makes more sense because of reliability. So in real life, you'll need both of them. That's just the way it is, and we have to live with that. So we'll show you some examples for wireline communication and some examples for wireless communications. I also want to show you the frequencies for the operations. At which frequencies does it operate for each of these different technologies. So let's begin with wireline communications. One example for wireline communications is to use wires, the twisted pair cable. I'm sure you've seen this in other electronic courses. And in general, in a twisted pair cable, your signal could be anywhere between 0 to 1 megahertz, right? So that's kind of the range for it. Another possibility would be, for instance, to use a coaxial cable. And a coaxial cable, so it looks like this, and we've used that in various courses of Sheridan. The range for your frequency could be anywhere between 0 to 500 megahertz, right? So and perhaps I should mention mega is 10 to the 6. I mean, you all should know this, the engineering notation mega. So kilo 10 to the 3, mega 10 to the 6, giga 10 to the 9, and tera 10 to the 12. These are some of the values that you'll end up seeing with frequencies. So just so you know. Okay. Another example of wireline communications is fiber optic. Right? So right now, fiber optic is very critical. Many of the homes that we have in the West, in Western countries, have fiber optics that reaches the home, and then your provider will give you a modem, and this modem is in fact connected to your fiber optic. If you don't have a fiber optic at your home, then probably you have a coaxial access at home, and therefore your provider will provide you the internet through your coaxial cable. So these are quite famous. With my family's home in Montreal, we have a fiber optic with Bell Canada. In here, where I am in Toronto, I don't have fiber optic. I have coaxial cable, and it's with Rogers. So it really depends on the provider and also on the region where you live and the type of upgrade that you've got to your region. Now, if we look at wireless communications, there are different wireless communication technologies. I'll go through some of them, and the way I'll proceed is I'll begin with the analog communications first, and then we'll move to the digital ones. So the most famous analog communications, as we noted earlier, is your radio, the radio that we use for analog communications. This is also the radio that you have, for instance, when you're in the car and you're trying to listen to some channel. Of course, I should also mention that if you're in the car and you're listening to something, the news, or you're listening to some music channel, the options are basically either AM radio or FM radio. But sometimes in the car, you also have the possibility to get XM and Sirius, right? These are satellite radio. XM and Sirius radio channel. Both of them are digital radio communications that are transmitted to you through satellite. They are not analog. These two are not satellite based. They are simply based on antennas that are within a certain region, and they have a certain coverage radius, and that's how you get the signal. So these two are analog, whereas AM and Sirius, these are radios, yes, true, radios that you get in the car, but they are digital communication radio channels. So anyways, these ones operate between this range, between roughly 500 kilohertz up to 1.6 meg, and then the FM from 88 meg to 108 megahertz. So both of them are analog. Another possibility of wireless communications is your 4G LTE. So I assume almost all of you are using this 4G LTE, unless you're fortunate and you have 5G. Although here in Toronto we still don't have 5G. It was projected to roll out later in 2020. That's before COVID. Because of COVID, it's going to be delayed potentially until 2021. But in general, this is what most Western countries have. They have 4G LTE, and the frequencies by which your 4G phone operates is somewhere between 1.7 gig, 1.9 gig, 2.6 gig. At least these are the typical frequencies that we have here in this country, in our country, in Canada. You also have 700 megahertz as well. 5G communications, or which also has the terminology, the technology around it, the radio access technology is referred to as NR, or new radio. The new frequencies that are proposed with 5G, not only in Canada, also in the US, in Europe, and in different parts of Asia, are 2.5, 3.5, and 28 gigahertz. And in fact, I have a lecture on this. It's posted on YouTube. You could listen to it. I go more in depth into it. But in general, there are two types of frequencies for 5G NR. There are those that are sub 6 gigahertz, those that are beyond 6 gigahertz. Those that are sub 6 gigahertz the famous two that are proposed are 2.5 gigahertz and 3.5. Today, here, us in Canada and Toronto, we do have the 2.5. It is, I believe, operated by Rogers, and the 28 gigahertz. This will be added potentially by later 2021 and possibly in 2022. The 28 will be for millimeter wave applications, so that's going to come in later on. Another example of wireless communications is your GPS, right? So you have GPS capability. Either you have some device, some GPS device that you have inside a car, or I would assume that you are using the GPS on your phone. So you, on your phone, in fact, you have different type of technologies. In the phone itself, that you have your cell phone, not because it's just a cell phone that you have one type of technology. Within the phone itself, it's a remarkably sophisticated device. You have in it a Bluetooth device and a Bluetooth antenna. You have in it a cellular device and a cellular antenna. Right? That's what you get you the 4G. And you have in it a GPS device and a GPS antenna. You have in it sometimes also for satellite radio, SATCOM, let's say for XM radio and so on. You have in it a Wi-Fi device and a Wi-Fi antenna. So this device in itself, it's highly sophisticated. You don't only have one type of antenna, you have an antenna for the different technologies that you have. Bluetooth, LTE, GPS, Wi-Fi, all of them are within this device, and the antenna are for each of them is in different parts around the screen. So one of the possibilities that you have with such a device is GPS, and GPS operates with two famous frequencies, L1 and L2. They have these designations, and these are the typical frequencies for GPS. Now I should mention that GPS is a U.S. technology. It is maintained by what is currently known as the Space Force. This is a new agency that was introduced by the Trump administration. Did not exist before, and they manage the constellation for these satellites. In Europe, there are another type of positioning technology. It's known as Galileo, and so that exists. There's another one in Russia known as GLONASS. There's another one in China. I believe India also have one. So there are different type of positioning technologies that exist, but I believe GPS is the most famous one, and it has a tremendous reach, and therefore many are familiar with GPS more than others. But just so you know, there are others as well. Satellite communication is also another possibility. So you might have satellite communications. You could have satellite communications for television applications. You could have satellite communications for different type of applications, for instance, navigation, for airplanes, for communications, for people that are traveling on an airplane. All satellite communication has those kind of applications. Right now, we're in 2020. There is this new area of 5G satellite integration, where we're using low orbit satellites to help the 5G network. So this is also a new paradigm of satellite communication. So this is also another type of application in channel. And the frequencies for SATCOM moves between 1 to 40 gigahertz. So the frequency is very, very high. Here we're AM, we are in the kilohertz. FM, we're mostly in the megahertz. All the other digital technologies, so these are analog, these and this are digital. As soon as we hit digital, all the applications operate in gigahertz. Well, I mean, you have some exceptions like this one here, 700 megahertz, but in general, all of the technologies operate in gigahertz in digital communications, in FM megahertz, and AM kilohertz. So this is kind of useful. Of course, AM also has some megahertz, but it's kind of easy when you classify them. That AMs are generally in the kilohertz, so 10 to the 3 hertz. FMs in the megahertz, so 10 to the 6 hertz. Digital communications, 4G, Bluetooth, Zigbee, SATCOM, GPS in the gigahertz, so 10 to the 9 hertz. And you also have in the terahertz the very, very fast, very high frequency fiber optics. Maybe I should also mention is that the higher the operating frequency, these things here are referred to as the operating frequency or the range for the frequency for the communication, the faster your connectivity. So if you look at this chart right away, you can say that fiber optics is extremely fast. And that's why you have a network of fiber optics in the oceans. So let's say you want to make a phone call between here, Toronto, to somebody in, I don't know, in Mumbai. And so the signal that you are transmitting, you might be using some mobile communications. You'll go to the tower. From the tower, you'll go to the mobile switching center. From there, it gets routed into cables of fiber optics in the ocean, literally in the ocean, between North America all the way to India. So this kind of gives you a sense of why fiber optics is heavily used. In fact, without fiber optics, I would have to say that the internet would not exist. Internet relies heavily on fiber optics. The fact that we have servers around the world and we're able to download and upload things to these servers and use and surf the internet, it's mainly because of fiber optics. So that's it. But let me just continue with the wireless communication technologies. Another technology that is extremely famous. This technology is remarkably famous. It's been around for some time, and it continues to evolve and to improve. And there are new standards that will be out regarding Wi-Fi soon. But in general, the ones that we have today, for most of us, is 2.4 gigahertz capability for Wi-Fi and 5 gigahertz capability for Wi-Fi. You have both options, and there are certain applications where you want to opt for 2.4 gigahertz, and there are certain applications where you want to opt for 5 gigahertz. So let's say you have a router and you are close to the router. You're very close. You're, let's say, that within the same room or within some line of sight. You will always opt for a 5 gigahertz. It will give you faster connectivity. But let's say you are still connected to the router, but you're farther away from the router and you have a bunch of walls between you and where you are to the router. Then the better option would be to go with 2.4 gigahertz. The 5 gigahertz will be very lossy. The quality will not give you a better quality. Although it's a high frequency, you expect a faster connectivity, but because you're far and you have a lot of
obstacles between the router and you would opt for 2.4 gigahertz. So this is kind of an interesting fact that is interesting to know. Another type of technology that we have in wireless communication and as a channel, in wireless communication channel, is Bluetooth. So Bluetooth is also a very known technology. This is one example, the earpiece, but there are other type of applications, and we've seen different applications. You've had perhaps some labs at Sheridan where we've worked with Bluetooth, and of course we also have Zigbee. So Zigbee is an application that is used. It's not the best application, Zigbee, this technology, the standard Zigbee. It does operate at 2.4. It's not the best. It has a reliability of 10 to the minus 3, so it's not very reliable. There's a lot of disconnected. I mean, the connection lacks it's not the best communication for high performance applications, right? So just to give you a sense, the Zigbee has a reliability of 10 to the minus 3. A Bluetooth is potentially around 10 to the minus 4, Wi-Fi 10 to the minus 5, and so on. So some of the technologies that have better reliability are certainly Wi-Fi. Wi-Fi is certainly better than Zigbee. But Zigbee is still around. It is mainly used for sensors purposes, and the device itself is actually very, very cheap. And I assume we've used some of them in some of the labs that we have. So this chart here gives you some of the wireless communication technologies that we have. There's another one as well. I added it here, V2X, and so vehicle to everything communication. Basically what it means is you have cars, and the hope is that these cars are not just cars driven by humans, but they are actually cars driven by robots, or they're autonomous vehicles. And these autonomous vehicles that operate, they are able to talk to each other. So V2X, it means vehicle to everything connectivity. If instead of X you put a V, so it becomes vehicle to vehicle communications. They operate at 5.9 gigahertz. So there are two famous standards in here, DSRC and C-V2X. But anyways, that goes beyond the scope of the course. It's just an area of research that I work on. So I hope that kind of gives you a sense of the different applications and how. So far we saw two important topics. We saw how to design a communication system, and we also recognize that in designing a communication system, you need to have the feasible modulation scheme. And then we said that in order to pick a feasible modulation scheme, one should know the type of channel that we are actually studying. And in addition to the channel, the application. Channel and application, they essentially go hand in hand. And we said that there are many channels that exist in communications. There are many applications that exist in communications. And we saw that on the previous slides. We realized that the channel could be wireline, it could be guided, or it could be non-wireline, it could be free. And it could be free in the air without necessarily being in a certain wire or in a certain medium. At this point, before saying that, we also saw the different frequencies for the different channels, at which frequencies the communication operates. And in particular, we showed you the different technologies in wireless communications, and we said wireless is more complex than wireline because it's very lossy. The communication is not guided. So as we saw the frequencies, I think it becomes more important to discuss the spectrum. And in doing so, I wanted to show you this slide here. To kind of give you a sense of the spectrum, how the spectrum is divided. So in the spectrum that we have, this electromagnetic, EM stands for electromagnetic, and the electromagnetic spectrum is divided as follows. So you have frequencies that are smaller frequencies, right? So it goes from smaller frequencies, essentially from 0 hertz all the way here. These are this is the spectrum. The spectrum is divided into different categorization. So here you have the radio wave, you have the microwave. This is the visible light, what we're able to see, ultraviolet, X-ray, gamma ray, and so on. At the end of the day, all these different type of classification, they essentially represent waves, and in reality, every sort of wave that you have operates at a certain frequency range. So even the voice, the sound that we have, humans, when we talk, the sound of our voice is anywhere between 20 hertz to 20 kilohertz. Right? I mean, it's at the lower end as well. So it's not really part of the E&M spectrum, but it's at the lower end. Okay, so that's the sound wave. But the electromagnetic wave, we could say it is anywhere from 500 kilohertz all the way to 3 times 10 to the 21 hertz. Okay, and as you can see, there's 2 classifications here. You have frequency, so this is the lower frequency that goes up to the higher frequency, and you also have the wavelength. They are related. They are related. When you talk of a certain technology or a certain classification of technologies, when you talk about the spectrum, you could either say the wavelength of a certain categorization or its frequency. They are interchangeable, and the relationship between them is based on this equation here. So C is equal to lambda naught F naught. So lambda naught is your wavelength, and F naught is your frequency. Usually I like to put a naught when we're talking about the operating frequency, the carrier frequency, and so this one would be the operating wavelength of a technology. And that's why I put the naught there. But this is the equation. And C is the speed of light. So the speed of light in vacuum, which is 3 times 10 to the 8 meters per second. So if you look at this equation, this means that the wavelength and the frequency, they are inversely proportional. So F is proportional to 1 over lambda. That's kind of what it means based on this equation. Okay, this will be useful, particularly for if you take wireless communications. We'll do a lot of work and analysis, and this sort of equation will be useful a lot when we do analysis. So let's move along. So the visible light is in reality this slice here. That I show you, and the visible light is essentially all the waves that we humans are built to see. So we are actually able to see these waves, and they allow us to see colors. In fact, the violet, the blue, the cyan, the green, the yellow, the orange, and the red, they allow us to see. And each of these different colors, they operate at a certain frequency. So TZH, this is terahertz, it's 10 to the 12, right? So you should realize that. So this is one type of spectrum that we as humans are built to see. Unfortunately, all the other type of spectrum ranges that exist, we are not capable. We do not have the capacity with our human eye to see them. So in fact, if we just focus, let's say on this range here, right? On this range here, from 500, roughly 500 kilohertz, could be a bit less, a bit more, but roughly 500 kilohertz, all the way to 300 gigahertz. This is where all the wireless communications live, right? So any wireless communication technology that we have today, it's in this range. It operates in this range. So we said kilohertz is mostly for AM technology, so it's about 540 kilohertz. Megahertz mostly for FM technology, and gigahertz is mostly for digital technologies. your Wi-Fi, your Bluetooth, your 4G, your 5G, your V2X, your SATCOM, your GPS, they all operate in the gigahertz. And you could, in reality, go all the way to 300 gigahertz, all the way up to here. In commercial applications, we don't have technologies that really operate at 300 gigahertz. This is very, very high. I think I mentioned it before. The higher the frequency that you have, the higher the operating frequency, the faster your connectivity. This is very, very high. Designing and building a device at a high frequency is expensive. It is not easy. It is expensive. And so we don't have it, right? It does not exist commercially. There are some government applications where they operate at really, really high frequencies. Right now, there is proposition of something called millimeter wave communications. And millimeter wave communications is part of 5G, and it will begin at the lower end of the high frequency. So it's around 28 gigahertz. And it could, in reality, extend all the way to 100 gigahertz, but not 300 gigahertz. 300 gigahertz is extreme. It's very high, but we might eventually reach here as we move through the different innovations in wireless communications. A lot of researchers work on high frequency technologies, and they want to bring us to capacities where we operate here. But in general, all the different type of technologies that you use, like your Wi-Fi, it operates around 2.4 gigahertz and 5 gigahertz, so around here, right? This is, by the way, logarithmic, the scale, right? You see that it jumps in increments. It jumps in increments. So it is a logarithmic scale. So from every tick to another, you are in fact going up by 100. So this is just the way it's not linear. Just so you notice. And the same thing on the other side. So for wireless communication applications, as you see here, it says wireless signals cannot be seen with the naked eye. We cannot see them, right? So you need a certain tool to enable you to see a wireless signal. And in reality, like I said to you, the only thing that they were able to see in the ENM spectrum, in the electromagnetic spectrum, is this very thin white slice here, which is the visible light. That's the only thing we're able to see. Microwave, we cannot see. Radio wave, we cannot see. Ultraviolet, we cannot see. X-ray and gamma ray, none of them we can see with the naked eye. We need a tool to enable us to see that. In fact, even things that are below, way below here, frequencies that are not in reality part of the electromagnetic spectrum, they also cannot be seen, like sound wave. Sound wave is not part of the electromagnetic spectrum. Like we said earlier, 20 hertz to 20 kilohertz, we still cannot see it with the human eye. We can only detect its impact. So detect the impact of a sound wave. So for instance, if you have a speaker, you put some small balls there, and then you run it. You run some operations, some song or whatever. You'll see the impact of the sound wave. But seeing it itself is not something that we're able to see with the naked eye. So if that's the case, what do we do? What do we do? We want to be able to see the frequencies of signals. It turns out that we have devices. These devices exist. This is one type of technology. In fact, this is the key technology that enables us to see wireless signals, but not to see them in time domain. In time domain, we're able to see these wireless signals using the oscilloscope. Right, so you have your oscilloscope that you connect, and you've all used your oscilloscope. That allows you to see a signal in time domain. But if you want to see a signal in the frequency domain, you need this tool. This tool is referred to as the spectrum analyzer. And in fact, in one of the labs, we go more in depth and explain it fully to you. And so there are different types of spectrum analyzers. If you see here, maybe the picture is a bit too small, but this is a spectrum analyzer that is connected with your USB cable. So it's a small one. It's an SDR, software-defined radio spectrum analyzer. So you connect this device here
to your computer with a USB cable, and then you download an application, and then the screen of your laptop kind of becomes your spectrum analyzer using this tool. I think this cost around $5,000. So it's not, I mean, it is somewhat pricey, but it's not as pricey as the ones that come in traditional like this, where everything is in fact integrated in one device. It's not a small unit that you connect to your laptop. So that's a possibility. In fact, since I'm talking about spectrum analyzer, I should mention to you that spectrum analyzers could range in prices. So, you know, this is, like I said, this ranges around $5,000. But in reality, some of the spectrum analyzers, you could also find them as cheap as $2,000 and all the way to $15,000. And some of them, in certain cases, could be up to $150,000. Right? So you go from something really, really cheap to something really expensive. So you might ask, well, hold on, why is it so expensive? Why is this spectrum analyzer so expensive? And like I said earlier, it depends on which frequencies it enables you to see them, right? So if you have a cheaper device, your capacity to see frequencies could be perhaps somewhere between, I don't know, 9 kilohertz up to 2.5 gigahertz, but not more than that. So you're really limited by a small range of frequencies, the lower end of frequencies, somewhere here, just somewhere here. So lower end of frequencies, not the higher end of frequencies. If you are looking at a really expensive spectrum analyzer, a spectrum analyzer that perhaps costs up to $150,000, well, these spectrum analyzers, they allow you to see signals that could operate anywhere from 3 hertz, which is a signal that is really, really low frequency, up to 67 or 70 gigahertz. 67, 70 gigahertz, that's tremendous. These are like very, very high frequencies that are potentially, and in fact they are used mostly by government agencies, but not by civilians. So this is it. This is what I wanted to mention. In fact, in this course, if we were in the lab, we would generally use 3 types of devices. The spectrum analyzer, this thing's here, that allows you to see the signal in the frequency domain. You also have the oscilloscope that allows you to see the signal in the time domain, and you also have a third device, which is your waveform generator, your function generator. Function generator is also another device that you connect, and this device basically, as the name goes, it generates different signals, like your sine signal, your sinusoidal signal, your square signal, your sawtooth signal, your triangular signals. These are different type of signals that a function generator could generate for you. And then that signal that you have generated, you could see it in time domain using oscilloscope, or you could see it in frequency domain using the spectrum analyzer. Now, you know, so I mean, these are 3 different standalone units that you need to buy each individually and then connect them together. One alternative would be to say, well, hold on, why do I have 3 different devices? Is there a smarter way of kind of integrating all these 3 devices into one device? So to be a bit more smart, like I said earlier, with a cell phone. A cell phone, you have your GPS, you have Wi-Fi, you have LTE, 4G LTE, you have different type of, you have Bluetooth, all of them integrated together in one device. So that's a smart thing. Instead of having one for each capability, you all have it integrated in one device. With measurement tools, you could also integrate them and have them in one device. But you could right away imagine the price could be very pricey. So you have companies like Keysight, Roden Schwartz, and Tektronix. They have some products where you have all 3 of them are basically put together. So you have all 3 of these devices integrated within one device, and that's also interesting to see. But of course, the price will be very high, and also don't expect the frequency to be as high as 300 gigahertz. Perhaps it's 1 to 2 gigahertz at most in terms of range.
but at least you won't buy 3 different devices. You'll just buy one, and you'll have it on your table as you do measurements. The question that one can ask is, well, like, how does this thing work? This thing here, spectrum analyzer, how it works? And the short answer is essentially given to you here. So the spectrum of signals is obtained using something called the FFT, or is the fast Fourier transform. Now, FFT is essentially a mathematical algorithm. It's just an algorithm that allows you to see it. And if you notice in the name, there's the word Fourier. And essentially, so I'll just let me put his picture. This is Fourier, Joseph Fourier. He's a French mathematician, and because of his work, we are able to in fact see the signal in the frequency domain. In fact, it is in general attributed to him, but most of the work that came from these devices rely on is really the kind of the work of a scientist, a researcher at Bell Labs, John Tukey. So that, I believe that was early in the 60s, and that came from his work. And in fact, Bell Labs, I think I mentioned it in lecture 1, is this tremendous lab in the U.S. And in the New Jersey area. And what they have done, so Bell Labs, it's used to be part of AT&T. Eventually, it became part of a company called Alcatel-Lucent. And today, Bell Labs still exists. It's part of Nokia, the Finnish company Nokia. And so this company is tremendous. In 1946, like we said, they came up with cellular. 1947, the transistor. 1948, digital communication with Claude Shannon. And around the 60s, you have such thing as the FFT, the fast Fourier transform, which essentially allows us to see signals in the frequency domain. So that's just another shout out to people at Bell Labs. I have some friends and some colleagues that work there, and they do tremendously interesting work there. So anyways, I hope that kind of gives you a perspective of the electromagnetic spectrum and how it all comes together. So if we were to summarize this, we as wireless people and people involved in communication, but particularly if we look at the wireless component of communication, not wireline, we are in this region. This is where we live, right? This is where we exist. So roughly between 500 kilohertz up to 300 gigahertz. All the technologies should be somewhere here, and we don't reach 300 quite yet. We are at most at 30 gigahertz, at least for civilian application, higher up to 100, perhaps even more for military and government applications. So that's that. On the next slide, I just wanted to introduce you to this guy here, Fourier. I'll show you a short video that talks about him, and then after that, we'll just continue. So I think at this point, with us being familiar with a spectrum analyzer and learning that one can see a signal in the frequency domain using this tool, it becomes a good segue to talk about Fourier. I think as electrical engineers, it is almost impossible to discuss anything related to frequency or frequency domain of a signal or a system without mentioning the name Fourier, right? So you'll hear Fourier series, you'll hear Fourier transform, and I think it's important to understand who is the man behind this tremendous mathematical tool that we as electrical engineers use all the time. So, like I said before, he is a French mathematician. He was there. He existed from 1768 to 1830, and this is a short video that was made by École Polytechnique in France. It's in English, the video, and I think it's an interesting video. It's a 3-minute video. I also will put the link there if you're interested to go get it from the sources on YouTube. So let's just watch it,
and then we'll move on after that. Okay.
You may have noticed that we're living in a world where technology is perhaps just a little bit important. You're watching this video on a phone, tablet, or computer with an internet connection, probably via Wi-Fi or 4G. And to make this video, a digital camera, microphones, and a whole host of different types of software were used. All of us, without exception, are required to send each other electronic signals. Of course, this modern world is not the invention of just one person. But if you'd like to thank someone in particular for all the little conveniences of your digital life, we have a good suggestion. Joseph Fourier. Young Joseph Fourier was a promising mathematician. He taught his first class at the age of 16 in Grenoble and became one of the first professors at École Polytechnique right after its establishment. This is what he is known for: the Fourier series and the Fourier transform. Not sure you understand? No problem. Basically, these equations are absolutely essential. They're the basis of all theories involving a signal. They bring order to the information. Take this video, for example. Without Fourier's equations, you can forget about compression. And without compression, the file for this video would be far, far too large, making it difficult to send. The image would become more and more pixelated before lagging and ultimately crashing. Fourier knew from the get-go that his discovery would be valuable to many different areas, particularly everything electrical. However, the mathematician had initially invented these equations to facilitate the study of heat diffusion. It was actually through studying heat diffusion that he discovered that atmospheric gases, their concentration and their nature, affect the temperature of the Earth. This notion, which we can see manifest today, is known simply as the greenhouse effect. And if that wasn't enough, he was also an explorer for Napoleon and participated in the French campaign in Egypt as part of the Commission of the Sciences and Arts. This resulted in him gleaning an enormous amount of knowledge on ancient and modern Egypt and on the country's geography and natural history. A series of books comprising 23 volumes in total was written to compile all these discoveries, and Fourier had the honor of writing the preface of this massive work. His passion for Egypt stayed with him for the rest of his life, and looking at his grave in Père Lachaise Cemetery, you almost forget that this was one of the greatest mathematicians of all time.
Like I noted earlier, the contribution of Joseph Fourier is extremely important for electrical engineers. Every time we work in the frequency domain, or we want to move from time domain to frequency domain, we always rely on his contribution, on his work. In reality, there are two key contributions from Fourier, as mentioned in the video: the Fourier series and the Fourier transform. I think it will be more clear as we move along, but very quickly, what we will see today in this lecture is the Fourier series. And the Fourier series is related to a continuous signal that is periodic. The signal is periodic. I'll explain this slide, and then I'll explain periodic, non-periodic. I'm sure you've seen it in other courses. By now you've taken some degree of courses, but I will give you a refresher on it in the slides after this one about periodic, non-periodic signals. But in general, his contributions are based on the Fourier series that are only valid for periodic signals, i.e. signals in the time domain, but these signals, they repeat. So let's say you have this pattern within this kind of window. In this would keep on repeating. It would repeat here and so on and so forth. It would repeat before. So you have time, let's say, it moves in this direction and it keeps repeating. So there's a pattern, this pattern here, and the pattern will keep repeating at every period of, so let's say, size p. Let's say this period is size p, and it keeps repeating. Sometimes if you have a signal that is not repeated, let's say a voice signal, let's say somebody's talking, and that signal of someone talking, this is not a repeated pattern. They are saying different words and different sentences as they move along, and therefore the pattern should not be repeated. And in such a case, the signal will be aperiodic. It won't be periodic. If we are working with aperiodic signals in the time domain, then we should always operate with frequency transform. Not quite frequency series. It's no longer an infinite series. It's called transform. Whereas if you have a pattern that keeps on repeating, then we work with frequency series. So if you use a function generator, and we said within a function generator, you could get a sine wave, you could get a triangular signal, you could get a sawtooth, you could get a rectangular, you could get a pulse. These are all forms of a shape in the time domain that keeps repeating. They have a specific period, and from the period you'll be able to determine the frequency of the signal, and then the signal keeps on repeating over and over and over again. You see a specific pattern that is repeated. In this case, for these type of signals, you will work with this thing here, Fourier series. Okay, so very briefly, in this slide, my objective is really to help you see or perhaps get a first glimpse of what Fourier series is. Sometimes when people study Fourier series in electrical engineering courses, they are given right away equations. And looking at equations are not necessarily easy to comprehend. They're a bit overwhelming, and right away you're hit with equations. I don't necessarily like to learn that way. I feel that the actual engineering concept is hidden. We don't get it. So the best way to learn is actually to learn the concept, to digest it, so to get an actual understanding of it, and then the equations and then the math will come in after that, and it will be more understandable. But if you see the equation first and then you don't learn the concept, it's not that trivial. So how do we see this figure? Where do we begin in this figure? There's a lot of information on this figure. Well, what we know so far, what we know is that we're able to look at a signal in the time domain. So look at this one only. Ignore everything else. Okay. So we're looking at a signal in the time domain. This is your x-axis. It's time. It's time. It's time here. And this is your y-axis. It's amplitude. It's amplitude. Okay. And in reality, when we look at a signal in the time domain, we have, like I mentioned, the time domain in seconds or milliseconds or whatever the case might be, depending on how fast or slow your signal is. Maybe, it's a measure of time. So the most obvious selection is seconds, but it could be a variety of what a second is by using engineering notations. And then the x-axis, you have the value of the signal. Now I'll call this signal S of t. S for signal, and then t because it varies with time. And these amplitude, the values that you see for the amplitude, they are voltage values. These are voltage values. Now, of course, you could also see the signal as a current signal, but let's stick to a voltage signal. So these are different voltages as you move along at time. So this is your signal, and you're able to see this using what kind of tool? So as noted before, and if you've done this in other courses, you're able to see this using your oscilloscope. This enables you to see your signal. So you generate a signal. Let's say you're using a signal that is generated, not something from the air with an antenna. From that generated signal that you get from your function generator, you then connect it to your oscilloscope and you see it there. Okay. So now that you see the signal, to you have no idea all the different information within it. There's so much information in this signal, but we don't have the lenses and we don't know where it is. It's kind of hidden in it. And so this guy, Fourier series, he comes in with a bunch of mathematical tools that allows us to kind of unfold this, to unpack this in order to see what's in this figure. And essentially what he's telling us is that he wants us to know what is the voltage contribution for different values of frequencies. So within this, you have different frequencies. You have some frequencies at the fundamental frequency, at F naught, at let's say 2 F naught, at 3 F naught. F naught is the fundamental frequency, the first frequency. And he wants to tell us with his equations, with his mathematical tool, how much voltage do we have in each of these different frequencies. Okay? And that's where the whole idea of an infinite series comes into place. So, for instance, in this picture, this is only in this picture based on this equation, you have a big contribution of voltages for instance, this one here, the third harmonic, right? The third harmonic, you have a big contribution of voltages. For the second harmonic, you also have a contribution of voltages, but it's not that big, right? So the value of it is smaller. Here it's a bigger contribution. And for the first harmonic, or if you will, the fundamental frequency, the contribution of voltages is very tiny. It's almost negligible. It's very small, very tiny. This doesn't mean you have this kind of pattern for every kind of signal. For different kind of signals, you will have different patterns. Sometimes the fourth harmonic is huge and the others are small. Sometimes the first one is huge and then the others are small. Sometimes all of them are large and the middle, let's say the 10th harmonic is small. It depends. It depends on what type of signal that you have and how the Fourier series representations is. Now, in the end, you break it down. You break down this signal into a bunch of sine waves and cosine waves, right? Sine waves and cosine waves. This is the most kind of basic way of representing a signal. A sine wave and a cosine wave. If you have a sine wave, you get an impulse. If you have a cosine wave, you get an impulse in the frequency domain. So how do you get this thing here? This thing here, the frequency domain. Well, first of all, you break it into small pieces. This signal, you try to break it into different frequencies, operating at different with different voltages. So with F naught, you have a small contribution. With 2F naught, you have this contribution. With 3F naught, you have this contribution. And if you add all of them together, you should get back to this one, right? So this is the sum of all these different contributions. Now, in the figure here, they didn't show you the fourth harmonic, the fifth harmonic. They didn't show you. Perhaps it exists, perhaps it doesn't, but they dropped it. They could not show it in the picture. But in the end, if you add all of them, and that's why it's called an infinite series, because you have an infinitely many of them, you add all of them, this should get you your signal back. So we take the signal, we break it apart, and you get all these different components. Now that we have these components, we'll be able to represent it, to project it on something on its frequency. So you look at this signal, and then you want to find the power level. What is the power of this signal? So in order to find the power, you need to find the peak value of the signal. It's a sinusoidal. You want to find its peak. You may also find its peak-to-peak value. And then once you find its peak-to-peak value, you want to find its VRMS value. And then once you find the VRMS value, which kind of makes you look at the signal as though it's a DC signal, and then you'll be able to use Watt's law to find the power. I'll explain all that. Don't worry. I'll explain all that as we go into the next slides. Also, it's in the problems that I solved in assignment 1. So you can look at assignment 1 and you could look at the answer keys. That gives you a hint of how to find the power of a signal. But I will explain it later on. And this power level is what gives the height of the signal. Right? So this has a small power level, small height. This has a large power level, large height. This height here, again, is not the value of the voltage. It is based on the value of the voltage. It is actually a measure of power measured in dBm. This is a measure of watts, dBm watt, or sometimes we just call it dBm. And the values that you have here on this axis, this axis here is frequency. This axis here is, I mean, here they say amplitude, but in reality, when you use a spectrum analyzer, you see it in power in dBm. Okay? And this essentially is your frequency domain. So this guy here, Fourier series, gave us a tool that nobody else thought of until he existed, of projecting a signal in time domain into frequency domain. And in order to go from here to here, you have to take it apart into various tones, various sinusoidals, and by looking at each sinusoidal, you'll be able to get the spike of it. These spikes for each of the sinusoidal. And the collection of these spikes, this is your frequency domain. So it's very powerful, and I think this picture it makes the understanding quite well. I think it gives you a good understanding of how we go from time domain to frequency domain. And in reality, this is all done automatically with your spectrum analyzer. So the spectrum analyzer that you have, the ones that I explained earlier in this presentation that I told you cost about $5,000, $6,000, that you connect with your USB cable, the ones that we have at Sheridan. This one, it does this in it. It does it automatically in it. You simply need to connect a signal to it, or you identify a specific signal, and it will get you the frequency domain. And again, the plot will be like this: frequency on the x-axis, and on the y-axis, it's a dBm, the power level. Okay, so let's move on. This is important in terms of notation. So sometimes you see these notations, and if you look at assignments 1 and assignment 2, you will see that I wrote things like this, right? So you are going from a signal. So let's say a signal has sometimes we call a function f of x. In this case, I called it s of t. It's a time domain signal, so it moves with time. So this is t, and the value of the signal, the notation for it, not the value, the notation is s. But this could be anything. It could be v, it could be p, whatever you want, right? It's just a letter. S, I just used it s because it sounds like signal. So s of t is this. It can be projected. You can see the projection, the one-on-one projection on the frequency domain. And if we want to project it on frequency domain, it's a convention that we use in engineering, is to take the same letter, but we write it in uppercase. So if it's small s here, we write it big S, and here you're looking at it in the t, because this is t, time domain. And here we look at it as a function of f, frequency. Okay? So this is frequency, this is time. So you're going from the time domain to the frequency domain using fs. What is fs? Well, fs is Fourier series. Or if you are given frequency domain, you'll be able to go from frequency domain to time domain. So it's bidirectional. You can go from one end to the other, and also from the other end back to its original state. So if I give you, for instance, this, you should be able to essentially get this, right? Essentially expressed in a series notation, right? Basically the collection of these ones. And if I give you this or this, you'll be able to get the frequency of it, right? So if you have s of t, you should be able to get s of f. And if you have s of f, you should be able to get s of t. And again, s of t is constructed by adding all these different tones. Okay, now to the scary part. Now this is the math part, so don't get too afraid. It will make sense when you solve the problems, right? So on an evaluation, I will always ask you things that you've seen in the assignment. So you'll see a variety of these different equations in the assignments. It's going to be more or less similar to the assignments. So maybe I should also mention the assignments. So for the first half that you are taking with me, we have 4 assignments. We have assignment 1, assignment 2, assignment 3, and assignment 4. So I usually post the assignments. In fact, I posted all the assignments to you, and I will provide the answers as need be. So as we gradually get into into an evaluation the week before a quiz or the week of that. Once you have the lecture and I think you're ready to solve the assignments at that point, and I assume that you have some days to look at it on your own, after a few days I will post the answers to the assignment. And in the answers we try to go in full detail, right, in the answers to the assignments. So for assignment 1, I already posted the answer keys. And assignment 1 essentially focuses on the power levels of a signal, and it also focuses on the time and frequency domain. So you'll be able to solve that. Assignment 2 is related. Assignment 1 is related to mostly to lecture 1 and some of lecture 2, but mostly lecture 1. And in fact, lecture 1 and lecture 2. Assignment 2 is related to the Fourier series, which is related to lecture 1 and lecture 2. Assignment 3 is related to lecture 3 and 4 for the AM. Assignment 4 is related to lecture 5 FM. So this is kind of the breakdown. So for your quiz 1, you're essentially responsible for the first lecture, the second lecture, this one here, and you're also responsible for assignment 1, not assignment 2. Okay, just assignment 1. That's for your first quiz. I hope that that's clear. Okay, and then for the next quiz, I'll explain what we will cover and what should be covered in that assignment. Okay, so let's move. Let me show you the equation. So, oops. So this is the equation. Okay, what you have here is the following. You have your signal. This is your signal, whatever your signal is. It looks like this in this case. It could be whatever is provided to you. As long as the signal is periodic, then you'll be able to use these equations. And let's assume the period is referred to as period P, but it could be, and in fact, generally the period could be in terms of pi, right? So 2 pi if that's the case, but it doesn't have to be. It could be anything. For instance, you might have a period that is 1, just a unit value, a 1, and you obtain a period of 1 because everything is normalized. So you look at it in a window of 0 to 1. If it's, let's say, a period is 2 pi, you look at it from a window of minus pi to pi. It depends. It's whatever it is. That's why in the equations, you don't see a 1 or 2 pi. You see letter P. So P is the period of where the pattern is repeated. So in this picture, this length here, this thing here, this is your P. This is your P. This is your period, right? So you measure it. You measure it. You put 0 here, and you see whatever value of time is here. This value, this is your P. Okay. And the equation is as such. You take the signal, and you could represent the signal in terms of sines and cosines. Sines and cosines with some different harmonics values in here. And you have a summation. Summation goes from 1 to infinity. Now, in here, we show you that the summation has an actual finite value of large n. But it could, in fact, in infinite series, from the name, it goes to infinity. It goes to infinity. But in practical applications, you will never look at a signal that goes to infinity. At some point, you say, that's enough. I'll stop here, and I don't need to look for beyond this precision. So usually you consider a finite value, but in reality, from the work of Fourier, this should be infinity, not a finite value. Okay, but in an engineering sense, we look at it in a finite way. And you have a bunch of sines and cosines. A sine, if you have a signal that is cosine or sine, it gives you only an impulse in the frequency domain. So that's the advantage of breaking a signal, a complex, weird-looking signal, into a bunch of sines and cosines. And if you look at the front of these sines and cosines, you have something called an and bn. These are referred to as the coefficients. How do you find the coefficients? Well, you need to use some calculus. You take your signal, whatever it is, you put it in here, you multiply it with the value with cosine of the inside that you have, sine of this, you integrate over a specific period, so you look at it over one period, and you multiply it by this as 2 over pi, and that gives you either your an or your bn. It's called an and bn because at the end, whatever result you get is as a function of the index n. the index n. In this part here, this is referred to as the DC part because there's no frequency here, right? DC part is whatever shows up here. When there's no frequency, this is referred to as the DC part. When there is only F naught, this is referred to, or n equals to 1. N equals to 1 is this, and this is only, it has a name. It's referred to as the fundamental frequency. And the others, they are the harmonics. This could be the second or the maybe the second is 0. I don't know. It depends on the cases. But if it is the second or the third, this might be the second harmonic or the third harmonic. I don't know what the case might be. And this is these are the terminologies that we use: second harmonic, third harmonic, and so on and so forth. Okay. And so all this will depend on the value that you have for your AN and your BN. And AN and BN, like we said before, these are values of voltages. What is the voltage contribution with this frequency? So this would be for instance, A3 and B3. What is the voltage contribution of this, and so on and so forth. I think it may look a bit unusual if you're seeing this for the first time, but when you solve the problem, especially in assignment 2 on this will help you a lot. But don't worry, assignment 2 is not on quiz 1. It will be, however, on quiz 2, but not on quiz 1. Okay, so I hope that that gives you a sense of what Fourier series is, how to move from time domain to frequency, and how to move from frequency to time domain. I mean, maybe one last thing that I should mention is the fact that sines and cosines are really more or less the same, right? So a sine is really a shift. I mean, if you want, you could. Sine of x could be represented as cosine of x minus pi over 2, and cosine of x is equal to sine of x plus pi plus 2. So it's a shifted version of each other. So shifting, when you look at it in the frequency domain, especially if we only look at the magnitude, we don't look at the phase, does not matter. So whether you look at a sine wave or a cosine wave, it will look the same. You just need to know at which frequency it happened and what is the value of this power. Okay, so that's that. I hope that makes sense. We'll do some problems. You'll do some problems as well in the assignments, and that should help you. Let's move on to the next slide. Before we finish this lecture, I just wanted to discuss a bit about some of the characteristics of electrical signals. I assume these are topics that you've seen before, but nonetheless, I wanted to show you, to kind of give you a refresher on it. So the first thing that I want to show you is this. So if you see here, this looks like a signal. It is a signal in the time domain, so this is perhaps something that you can see on an oscilloscope. And the first thing that we identify is, of course, in a figure, is the axes, right? So this axis has t, so time, and this axis has some characteristics, x of t. And we said if we are looking at an electrical signal, this is time in seconds, and what you see in the amplitude is actually values of voltages. So sometimes it could be current, but that's what it is. Now, if you notice on this graph, you have so many different possibilities for the value of amplitude, right? In fact, because there are so many different values of possibilities, it's continuous in that sense. We say the more accurate way of saying this is that there are infinite number of amplitude levels. On the y-axis, there are infinite number of amplitude levels. And because of that, this signal is analog. So when you look at an analog signal, you really pretty much look at not the x-axis, you look at the y-axis. Analog digital is decided by the y-axis, by the levels of voltages. So here there are, it's not at discrete points, there are specific values at all the possible values, and therefore there are infinite levels, and therefore this is an analog signal. An analog signal, like I say here, is something that you could enter into an analog modulator, right? Examples of analog modulators, we saw it earlier, AM, FM, PM, PWM, these are all examples of analog modulators. FSK, PSK, all this, these are digital modulators. This would not work if you put it inside it. It would not work. Okay, next, here we show you an example of a digital signal. Now, why is this digital? Well, just by looking at it, it gives you a hint that it's digital. But to think conceptually why it's digital is because you're looking at the y-axis, and then you see finite number of levels. So you have one level here, one level here, one level here, and one level here. In this case, you have 4 levels, right? So there are finite number of levels, whereas here there are infinite number of levels. If you could keep chopping it, there are infinite number of levels between this and here, whereas here there are simply 4 possible levels of voltages. One level of voltage here, whatever the value is, one level of voltage here, whatever the value is, and then on the negative side as well. And because of that, again, we're looking at the y-axis, this is referred to as a digital signal. And this signal is something that you could also see in an oscilloscope. You have your time domain here, you have your axis in time on the x-axis, and voltages on the y-axis. Such a signal is a signal that you could actually enter into a digital modulator. So if you are talking of digital modulators, we talk about BPSK, QPSK, QAM, IQ QAM, it's kind of an extension of each other. FSK, these are all examples of digital modulation. So if you have a digital modulator entering this, would work. If you enter this into an AM or an FM, it would not work, right? It would not, or perhaps it could work, but it would not give what is expected. So yeah, so that's that. So with an analog signal, it works with an analog modulator. Digital signal, it works with a digital modulator. And in fact, the number of levels, maybe I should mention this, the number of levels that you have with a digital signal, they should follow the expression 2 to the k. So it has to be 2 to the power k, and then k is just a bunch of integers, 1, 2, 3, 4, 5, all the way, a bunch of integers, positive integers. So the number of levels could be 2 to the 1, which is 2 levels. The number of levels could be 2 to the 2, 4 levels, like here. We have 1 level, 2 levels, 3rd level, 4th level. The number of levels could be 2 to the 3, 8 levels, 2 to the 4, 16 levels, 2 to the 5, 32 levels, and so on and so forth. You can never have, for instance, a digital signal with, let's say, 3 levels. Not possible. You cannot have a digital signals with 5 levels, 6 levels, 7 levels. Not possible. It does not work with 2 to the power of some integer. So the possible number of levels of 2, 4, 8, 16, 32, and so on. So this is something that you could be that you should realize. Now, in this case, again, in this example, we have 4 levels: 1 level, 2 level, 3rd, and 4th. This is not a level. The 0 is not a level. It means that every level can be characterized by 2 bits, 2 bits of information. So, for instance, this level, if you get anything here, it could be characterized by a 0, 0 bit. So anytime you have a voltage that represents this, you could send in your digital modulator. What enters a digital modulator is basically, for instance, it could be 0, 0. This level, you could enter a digital modulator as 0, 1. This level, you could enter in the digital modulator as 1, 0. This level as 1, 1. Okay, so that kind of gives you a sense of that. And this kind of also falls into some of the topics that you saw in DP1, Digital Principles 1. And again, these are this thing here is part of the second part of the course, and this is mostly this part of the course. Okay, let me show you other type of signals that you might encounter. So here we talked about it earlier when we talked about Fourier series. We talked about periodic signals, and this is an example of a periodic signal. So a sine wave is a periodic signal. A cosine wave is a periodic signal. This picture here, this signal here, kind of a triangular with some clipping here, this is also periodic, because if you see this pattern that you have here, is you could literally take a copy and paste it everywhere else before and paste it everywhere else after. So it's just a carbon copy of this that you could put everywhere else. This pattern keeps repeating. And when you have a periodic signal, the first thing you need to ask yourself is what is the period? To find the period, it's just to find the pattern that keeps repeating. So for instance, you could say the pattern repeats itself from this point all the way to this point, or you could say the pattern repeats itself from this point all the way to here, or you could say that the pattern repeats itself from here to here. It depends. You choose what it is. In the end, the period is equal to T naught. So for me, what I decided in this picture, I'll take the period from here to here. It doesn't matter as long as you go from one identification of the pattern to the other. For instance, from here to here, that should also be T naught. Okay, and this kind of gives you an equation that shows the periodicity of a signal. Right. So if you shift it by T naught to the back or to the front, if you do minus to the front, if you do plus to the back, it will still give you identical. It will be identical. So this is a periodic signal. And we said when you have a periodic signal in the time domain, then certainly you have no choice but to use Fourier series. Okay. If you want to move into frequency domain, you have to use Fourier series. And finally, I want to show you an aperiodic signal. Sometimes also we use the word non-periodic. So it's just, this is periodic, non-periodic. So, but the fancier way of saying non-periodic is just aperiodic. And if you have an aperiodic signal, well, what you do is the following. You look at the shape of your signal, and what you identify in this signal, there is no specific pattern that is repeated. The pattern itself is not repeated in a specific way. It's like a sound voice. So if you're saying different words in different sentences, then there is no specific pattern. But if you keep repeating the same word over and over and over again, like I'm saying right now, over and over and over, it's just I'm repeating the same word, there will be some pattern to it. It will look more or less the same. But if you're talking naturally and you're using different words, different sentences, the signal is not periodic. It's an aperiodic signal. There is no specific pattern that is repeated over time. It seems unique at every single time. Okay, and if you have an aperiodic signal and you want to look at it in the frequency domain, well, in this case, Fourier series would not work. You have to use something called Fourier transform. So we don't cover Fourier transform in the first part of the course. We'll cover it later on, potentially in the course, but not in the first part. But just so you know, you would work with Fourier transform. Okay. On to the next slide. On the previous slide, we talked about analog signals, digital signals, periodic signals, and non-periodic signals. Now on this slide, I'd like to continue and then discuss a bit of the characteristics of specifically sinusoidal signals. So based on what we saw from Fourier series and Fourier transforms, we learned that all electrical signals can be represented as a combination of sine and cosine waves, all of them. And so you bring any type of electrical signals, and then we'll be able to take it apart and represent it in terms of different sines and cosines that can be added together to form the original signal. So that's what we know from Fourier. Now, also maybe I should mention, and perhaps I did mention it before, the relationship between sine and cosine should be obvious, right? So a cosine is pretty much a sine. A cosine is simply a sine that is just shifted, right? It's just shifted by pi over 2. So this is kind of the phase. And in fact, when we look at the spectrum, when we look at the frequency domain of a sinusoidal, it does not matter if you are looking at whether it's sine or cosine. It will be the same, because in the spectrum, in the frequency domain, the phase is not shown. We only show the amplitude. I think this will be clear later on in this slide, or perhaps the slide next week. But this should something that you should also add to your body of knowledge. So since they are the same, I guess my objective here would be to use one or the other. It's quite common to consider the sine as opposed to the cosine, but if you want to do the same analysis with cosine, it does not matter. They're pretty much the same, except there's a phase shift, and as we said, phase shift is not that important when we consider the magnitude in the frequency domain. So let's consider a sine wave. And let's just see some of its characteristic of a sine wave, of a sinusoidal. So let's just call it S of t. So S is just an identifier to this signal in the time domain. A naught is the amplitude of this signal. Sine is the sinusoidal itself, and omega naught t. Omega naught it's a constant, and this is known as the radial frequency. And t is just the variable, right? The time that of which the sinusoidal will move on. So this is something that you'll be able to see, for instance, with your oscilloscope. So let's put it together and let's see its characteristics. Let's see what we could actually observe from a sinusoidal. And we're doing this because sinusoidals are very critical. Like we said here, all signals, all electrical signals can be represented in terms of sine and cosine. Therefore, understanding a sine or a cosine becomes very important. And that's why I wanted to show you this slide. Okay, so let's see how it is. So here we have your signal. You have a sinusoidal signal. This is a sine. Therefore, it begins here and it goes into a cycle. And it's a signal that is periodic. So it's not a sinusoidal that is aperiodic. Sometimes if you have a sinusoidal that is aperiodic, you might just have one period, and that's it. It doesn't continue. But in this case, it is a periodic sinusoidal. So which is kind of the definition of a sinusoidal. It goes on and on and on forever on the positive and also on the negative. So it's a periodic signal. And of course, if you look at this signal, there is no finite number of levels. When you look at the y-axis, there's infinite number of possible values that you could get, and therefore this is an analog signal. This thing that you see here is an analog signal, and it is a periodic signal. So let's try to see some characteristics. Well, first of all, we are looking at it in the time domain. The measure for time domain is seconds, and this is in the voltage. So the magnitude, it's voltage. And what else do we identify? Well, we could right away find the amplitude for the signal, right? So the amplitude, this here, A naught, is actually here. This is the amplitude. You could also show that the same thing happens on the negative. So it's the amplitude, but there's a minus in front of it, and that's the minus. Okay, so that's kind of obvious, and I'm sure you've seen this in other courses. This was just kind of a review for you. What else can we identify? Well, the other thing that we could right away get from the picture of a signal, and of course you could do all this with your oscilloscope, is you could put a cursor and then you could find the period. The period is right away the cycle. So this is one cycle, and then the pattern repeats itself. So therefore, this thing here, it gives us the period, and therefore this is the period. This is the period of the signal. And the period is always represented as t. I like to put naught. So t naught is the identifier for the period. It's a measure of time, and that's that. So we don't write small t. Small t is for the generic one, and large t is for the period. And once you have the period, you could right away find the frequency of the signal. And once you have the frequency of the signal, you could right away find the radial frequency. And I'll show you all this in a second. What else can we identify here? Let's move along. Well, we could certainly notice the V peak. So the peak value of the signal. And in fact, V peak is equal to the amplitude. So the V peak of this sinusoidal is equal to your amplitude, to your A naught here that you have. So they're the same. Okay. We could also find the peak to peak value. And that's why it's written V peak to peak, from one peak to the other. And basically V peak to peak is equal to 2 times V peak, right? V peak to peak, 2 times V peak. So, and again, I am almost positive that you've seen this in other courses, but every semester there are a bunch of students that come in and then they tell me they forget these terminologies, and therefore I find it important to actually spend the time and explain all this to give you a refresher so that you don't forget, and hopefully you'll use it for the labs and also for your assignments and for your quizzes and for your midterm and final. So this is a very useful knowledge that you will need. Not only in this course, by the way, in other courses as well. Okay, so what else we could do is, well, certainly we could now jump in and find something called the RMS value. So the RMS value, I mean, you could think of this, I mean, this is an alternating current signal, right? So it's a signal that has a frequency. And if you want to kind of see the same effect of the signal, but instead of having an AC type of signal, you want kind of like a battery equivalent of it. What would the voltage be if you were to represent this AC signal in a battery equivalent? And what would the voltage of it be? And this is what RMS is, VRMS. RMS stands for root mean square. And what it is that it's this equation here. So you integrate over a period, which is, this is your period. And you integrate over the duration of the period. So let's say from 0 to T naught. And you do 1 over T naught, and inside the integral you take the signal, whatever it is. In this case it's a sinusoidal. Some other instances it could be whatever signal is provided to you. You square the signal and you do the integration with respect to t. So here what I wanted to show you here is that in fact you could simplify your life a bit, and instead of doing the integration for an entire cycle, you could actually do it for half of the period. Right? So you could do it from 0 to T naught divided by 2, which is up to here, and the bottom, this one here, and this one here, they will essentially be the same once you square them. So if you square this bottom part, it will show up here. So you'll have two kind of mountains, one mountain here, another mountain here that is squared. So therefore, it's going to be a bit higher. And so why do it twice, right? Don't forget integration from calculus. We know integration is basically finding the area under the curve. So if you square this, it's going to be positive, and the area under this part of the curve and the area under this part of the curve will be the same. So you could just do 2 times that and then just look at it from half of the period. So you do that, and don't forget your square root. You do some steps, maybe you'll spend some time. I just did it on paper, but I didn't have time to put it here. I know the answer, but I just wanted to see that I'm still sharp with calculus, and maybe you could do the same thing. You would essentially get the following. So you'll end up with A naught divided by square root of 2, and as we said, A naught is basically your V peak. So the important result is that your RMS value is equal to V peak divided by square root of 2. And this is important. And if you don't like this, you could just remember that it's roughly 0.7 V peak. So your RMS value is about 0.7 V peak. That's what you need to remember. And that's why I drew the line here. This is where it would be equivalent if you had a DC battery as opposed to this kind of alternating signal. Okay. You should, however, remember that this representation that we have is only true for a periodic sinusoidal signal. So if you have a sinusoidal that is non-periodic, let's say it just stops here and then there's nothing after that and nothing before that, this would not work. And if you have a something else, maybe a sawtooth signal or some other signal, it's different. You have to show it to show that the result is the same. So you have to show that. There are some tables on this, so it's not necessary that you do the calculus every single time, but this is a skill that is needed, and you're all like you've all have done calculus, so this is also an interesting exercise for you to see if you're sharp with your calculus abilities. So just remember, this is only true for a periodic sinusoidal signal. Does not matter if it is sine or cosine, this will be true, but not for anything else. For anything else, you have to show it or look at some table that gives you that. Here, what I want to show you is the following, is that if somebody gives you this expression and then you are told what is the period, you could always find the period from this. And you could always find the frequency of the signal from this. Or so what you do essentially is you always could go back to here. So if, let's say, we have this expression, this thing here, the radial frequency, is equal to 2 pi f naught. Right? So the unit for the radial frequency is rad for radians per second. And then you could just divide by 2 pi, and then this allows you to find the frequency of the signal, right? And the frequency of the signal, of course, has the unit hertz. And once you find the frequency of the signal, you can then find the period. The period is just 1 over the frequency, and the units for the period is in seconds. So if one gives you an equation and you're asked to find the period, this is what you do. You go from here, from the radial to the frequency, and from the frequency to the period. On the other hand, if one gives you a figure, a picture, a graph of a signal like this, right away from the graph you could find your T naught, you could find the period here, and once you find T naught, you can find the frequency. You just do 1 over of the signal, and once you find the frequency, you can find the radial frequency of it. You just multiply by 2 pi, and then this value, you enter it into some sinusoidal, sine, cosine, doesn't matter. If you do this in an exam, I would accept it. I would prefer that you use sine, but even if you write cosine, for me, it's still fine. You would just enter the value here, and you just put a t in front of it. So you could always go from a graph, a picture of a graph, to an expression for a signal, or you could go from an expression of a signal to a graph of a sinusoidal. So, and again, all of this is possible because of these 3 lines, right? Don't forget these 3 lines. This is where people and students mess up and they do mistakes. What is period? What is frequency? And how is frequency and period related? Well, just 1 over T naught. What is radial frequency? How is your typical frequency and radial frequency related? It's like this. What are the units? Don't forget the units. People lose marks because they forget their units. So that's what I wanted to show you here. This is perhaps for some people just a refresher of some of the topics that they've seen related to signals. Maybe in AC circuits you've seen this, and in other courses as well. But I just wanted to add it just in case you forgot and you needed a refresher. Let's continue. So I guess now that we have the VRMS, then it will be useful for us. And in fact, you might ask, well, why did we even bother to get the RMS value? Well, we found the RMS value of a signal just because of a sinusoidal, right? The RMS value, the RMS voltage of a sinusoidal, because this RMS value of a sinusoidal will be useful for us to find the power of the signal. And we did all this just because we are interested to find what is the power of this signal. In telecommunications, power is everything. Power tells us how the quality of a signal is. We will later on talk about SNR and SINR, and this is a metric for the quality of a signal. And therefore, when you measure these things called SNR and SINR, power is what you're looking for. Therefore, knowing the power is necessary. And without RMS value of a signal, we will not be able to find the power. We will not be able to use Watt's law, which you've seen in electrical fundamentals, especially if you've taken the course with me or with other instructors. You've seen how we could find the power of the power. What's the equation of power? So it's known as Watt's law. And using that, you will be able to find the power by using the DC equivalent of the voltage. In this case, the DC equivalent of an alternating current signal is just the RMS. And therefore, that's why we found the RMS. And I'm going to show you how to find the power on the next slide. we are running over time. I do recognize that, but on the next lecture and next week, I'll present less, and so it will be regulated in that way. Okay, move on to the next slide. Now that we obtained the RMS voltage of the sinusoidal, we are really equipped to find the average power of this sinusoidal signal. And in fact, it would work for all different kind of sinusoidal signals. So let's begin. What I will do is I will just bring the same description of the signal that we showed on the previous slide, and with the representation of it, the mathematical representation of it. And let's begin. So number one, we could immediately go back to fundamentals, the fundamentals of electrical engineering, and we could simply go back to the Watt's law, right? So Watt's law, it is attributed to James Watt, the Scottish mechanical engineer, where we know that the power could be represented in three different ways. Basically, the most easier way to remember Watt's law is just voltage times current. Or if you play around with some Ohm's law, you'll figure out that it's equal to I squared R. So I squared times the impedance or the resistance, or it's in fact equal to the voltage squared divided by the resistance. So, and what you notice here, we said it's the average power. Because it is the average power, we are in fact using everything with RMS values. Right? So we're using everything with RMS values. The only thing that is not RMS value is the resistance. This is an actual resistance. It's in fact referred to as the input resistance of the spectrum analyzer, and this is an actual resistance. I mean, sometimes we call it impedance, but in reality, it's a resistance of that you have for the device. This device that we use, the spectrum analyzer, that allows us to see the signal in the frequency domain. Okay, so if we look at the different varieties of the Watt's law, whether this one or this one or this one, the one that we can work with is certainly this one. This is the best. We have everything about it. The RF input impedance of the spectrum analyzer, this could be fine. We could find it for a specific spectrum analyzer that we are using. The RMS voltage, we already know, right? So we know the RMS voltage for a sinusoidal. It is simply the V peak divided by square root of 2, which is, like we said earlier, if we don't like to know this, we could just remember that it's 0.707 V peak, or if you don't like that, you just remember that it is roughly 0.7 V peak. So we have that. We could just enter it here, square it. Don't forget your square, and then we divide by the input resistance of the spectrum analyzer. Okay, so if we look, for instance, at the spectrum analyzer that we have, which is the Tektronix RSA306B, and the value that you could find in the data sheet is 50 ohms. 50 ohms for the amplitude, right? And that's exactly what we want. This is exactly what we want. The input resistance is this. Whatever the value is, right? It depends on what you're using. So depending on what type of spectrum analyzer you use, you could just look at their data sheet and then figure out what the input resistance is. For us, we're using this one here, the Tektronix one, which it operates between 9 kilohertz up to 6.2 gigahertz. So in other words, it would work for some of the famous wireless technologies. Your Wi-Fi would work here, your Bluetooth would work here, your Zigbee would work here, and some of the other technologies would also work here, your AM, your FM, they would all operate with this spectrum analyzer. So it has certain capabilities here. But as soon as you go beyond 6.2 gigahertz, then this is pretty much useless. This device is useless. It will not work. It will not be, it won't allow us to see it. But for us, for the applications that we have in school, this is fine. So that's it. So we have the VRMS, which is just V peak divided by square root of 2. we have the input resistance, which is this, and therefore we will be able right away to determine the average power of this periodic signal. Okay, and this equation here is true for different type of periodic signals. So this equation that you see, the Watt's laws with RMS notations, they are true for all kind of sinusoidal signals, whether it is all kind of periodic signals. Sorry, I did not mean sinusoidal, but all kind of periodic signals, right? So if you have a sinusoidal, this is true. If you have a sawtooth, this equation, these set of equations are true. If you have a square wave, periodic square wave, they are true. Triangular square wave that are periodic, they are true. If they have pulses, pulse signals that are periodic, it is true. If you have a sinusoidal that is periodic, like we see here, then this is also true. As long as it is periodic, then these equations are true. Okay. And now I just want to open a sidebar here and maybe discuss how to go from watts to dBm and from dBm to watts. And this is important because in reality, when as electrical engineers, many of the different measurements that we do with devices, such as this one here, the Tetronics, or in fact, all kind of spectrum analyzers that you would buy, whether from Rohde & Schwarz, Tektronix, or others, they would all have the measurement in dBm. In fact, not only these devices, even if you do simulations with MATLAB, right? You do simulations with MATLAB, let's say you use Simulink, it will also display the result in dBm. So how would you make sense of dBm? The measurements that you get from here is in watts, right? So this is in watts and this is in dBm. So how do you move from dBm to watts? Well, this requires some skills. Different people will show you different equations, but in reality, for me, I think the most critical ones are these three, right? So you should, in fact, know that anytime you work with watts, this is known as linear data. And if it is linear and it's a power measure or it's a power difference, then you would simply enter it into a log base 10 and you multiply by 10. Okay, and that gives you the result in dB. So if it's a power difference, it would be in dB. If it's a power, a measure of power, and the input is a watt, then this would be dBW, dB watt. If the inside is a value in milliwatt, then this would be dBm, right? dBm, or which basically stands for dBm watt, but for some reason the W is dropped. We just write it as dBm. And let's say you are given a value in dB and you want to go back to a linear format. What you do is you simply solve for linear, and this basically means that you do 10 to the power of dB divided by 10. Okay, and that gives you the value in linear. Now let's say you get some value in dB watt and you want it in dBm, or if you have something in dBm and you want to move to dB watt, well, you could simply remember this, right? So you simply add 30 to a dBW, and that gives you the result in dBm. So that could be also interesting if you want to memorize. So to me, these three equations are enough for me to deal with dBs and watts, and I think it's the same thing for you. So I solved many of these questions related to dB and dBW on assignment 1, and in fact we have a bunch of questions related to this in assignment 1. So please go through them. I would assume this is something that you've seen before, but if not, then please go through them and see that you're doing this appropriately. This is an important skill that we will use in this course and in other courses as well. So at this point, I think we're equipped to right away go back and wrap up the story, put it all together, and basically go see how we form the frequency domain, right? So we go back to Fourier series and figure out how to put together the frequency domain. We have all the different small items needed to put together the frequency domain, okay? So we'll continue that on the next slide. So now we obtained an expression for the average power for the sinusoidal, we're ready to go ahead and show you how the frequency domain of the sinusoidal is obtained. And the objective that I have in here is really to show you how to look at it in the time domain and also in the frequency domain, and to give you the expressions needed in such a way that is compatible to what you would end up seeing with the spectrum analyzer. What exactly do you see with the spectrum analyzer? The same thing. We want to be able to express it analytically. And that's the whole point of this slide, and then the one after that. So just to recap, in time domain, a sinusoidal can be expressed as such, right? So what you have is essentially the amplitude. I just wrote it as V peak, and you could have sinus sine omega naught t. Omega naught is the radial frequency plus some phase. Some people may also use cosine, and that's fine as well. It is also a sinusoidal. Sine and cosine, they're fine. So instead of sine, they might write cosine of omega naught t plus some phase. And so I just gave them two different identifiers, S1, signal 1, and S2, signal 2, just to let you know that they're different, because they are different, but they're quite similar in a spectrum, in a frequency domain perspective, right? So don't forget, when you look at these signals and with a spectrum analyzer, there is no information about the phase. You only see on the y-axis the magnitude of your signal, the power, the magnitude of the signal power on the y-axis in dBm, and you only see the frequency on the x-axis. You have no idea about the phase, and therefore the phase is not important. But I'll show you nonetheless why this is the case. So imagine somebody uses a cosine. This is what we get. And if you look at the expression, we said that a cosine and a sine is essentially related by simply adding pi over 2 to the inside of to the inside of the cosine. So if we take the inside of the cosine, you add pi over 2, then you'll be able to write it as a sine instead of a cosine. It's just a shift of one plot with respect to the other, of cosine and sine. And if you want to, I don't know, use a different notation, let's call this as some new phase. Let's call it phi with a tilde. And then you'll be able to basically write it as such. So Vp is the peak, and you have the sinusoidal, and you have the radial frequency, and you have this. So if you compare this and this, they essentially look very similar. The only difference is that the phase is different, and we said the phase is not important when you look at such a device. Such a device will never show you this or this. So even though they're different from the phase, this thing here does not care. It will not show you the phase. Okay, so I kind of explained this multiple times. I hope it's important because students come back to me with these questions all the time from experience. Well, what happens? They are not the same they're not the same signals. Why do you say they're the same? And I agree, they're not the same, but the difference is really the phase. And again, the phase will never show up with a spectrum analyzer because you only have the magnitude of the signal, the power signal over the frequency. Okay, so that's what we get. This is what we have in terms of the expression for the sinusoidal in the time domain. Now let's look at it in the frequency domain. So how can we write some expressions in the frequency domain? So I'll show you what we do. So if you look here, we have an expression, and we said that when you have some signal, you could show its frequency domain equivalent by simply writing big S. And here I wrote V because we're looking at it from a voltage point of view, not power quite. That's why I wrote the V here, the sub with V, because we're looking at it with the voltage. And it's a function of frequency. And you have the 2 bars. 2 bars, it means that you're looking at the magnitude. That's what it means. And then we open the bracket. And if the frequency equals the actual frequency of the signal, which is this thing here, and don't forget, we said that the actual frequency of a signal is related to the radial frequency. How is it related? Well, in this case, if I give you the radial frequency, you'll be able to simply find the actual frequency by dividing by 2 pi. That's how it's related. So at this frequency, you have the actual amplitude, the amplitude of the signal. At any other frequency, so at f not equal to f naught, otherwise, some people don't even write this, they just write otherwise. So any other frequency that you have, you'll end up getting a 0 here. Okay, so I hope that that makes sense. This is just a mathematical way of writing the frequency series of this one here, this or this. For both of them, whether you use a sine or cosine, this is the frequency series equivalent by looking at it with voltage. Now, what do I mean by voltage? Well, it basically means something like this. If you look, remember this figure that I showed you earlier when we talked about Fourier series? We said you have some signal, some complex signal, you take it apart, you will look at the different signals, the different amplitude and frequency, the different amplitude contributed by each of the different frequencies. So this is f naught, this is 2f naught, this is 3f naught. And if you look at this picture, this line here is the amplitude in volts. And the same line is also used in the frequency domain on this picture. And that's why this expression is very compatible with this image that you see here. Because this line here, this y-axis for the frequency domain is also in volts. It's not in power. And then this one here, the x-axis in the frequency domain, this is in frequency. But if you look at a spectrum analyzer, the spectrum analyzer does not give you the value in voltage. The y-axis with the spectrum analyzer is not in voltage. The actual value with this one or any other spectrum analyzer, it's always in dBm. So how do you change this in dBm? Well, you do all the stuff that we talked about earlier. You take your voltage, you find the RMS voltage. Once you find the RMS voltage, then you use Watt's law to find the average power. Once you find the average power, then you use some dB exchange, so you change it into dB watt. Once you change it to dB watt, then you can change it to dBm. And this is what you see with this device. So let's just do it. Let's just do it together so you see what I mean. So instead of this, we could actually express the result as such. This is exactly how you would see it with a spectrum analyzer. You have your spectrum, so you're seeing in the frequency domain. Here I write sub P because we're looking at it with respect to power, P. Here we're looking at it with respect to voltage, V. But we said V is not shown in the spectrum analyzer. That's why we use P for power. And we show that there are two possibilities. One option is essentially the value of the frequency domain is the power in dBm at frequency equals to f naught. And how do you find f naught from this? Well, you just divide by the radial frequency by 2 pi, right? Here, and for any other frequency, it's equal to 0. Okay, so this is really what you end up seeing here. So again, this and this are together, this and this are together. Okay, so this is related to the spectrum analyzer, and this in this picture, they are related together because this shows it in the voltage. I hope this is clear. So let's see how to find this value here, the power in dBm. Let's do it together. So the following is what we do. We begin by saying that the power in dBm for the sinusoidal is equal to the power in dB watt plus 30. This comes from the equation that I just showed you earlier. Okay. Next, what do? Well, we know that the power, the power of the signal in dB watt is basically equal to 10 log 10 of the average power, and then your 30, you just carry it here. Okay, you just carry it next to it. Okay. Next, what do? We need to figure out what is the average power. The average power is equal to 10 log 10. And the average power, we know from Watt's law, is equal to the voltage, the RMS voltage, squared over the internal resistance of the spectrum analyzer. This thing here, the internal resistance of this thing. And we said generally it's around 50 ohms, according to the data sheet of the Tektronix one. But if you have a Rohde-Schwarz spectrum analyzer or a Keysight, you could just look at their data sheet, and then whatever it is, you put it here. By the way, when I say Rohde-Schwarz, Tektronix, or Keysight, they have many of these spectrum analyzers. You have to look at the specific one that you are using, right? So there are many of them. There are two things that you have. There are many features in a spectrum analyzer. In general, when you buy a spectrum analyzer, you're trying to buy one that gives you a certain range of frequencies that it works with, and a certain range of power that it works with. Okay, so you have to make sure on that. So you look at the ones that you have. For us, we have this, and therefore we look at this. Here, I just put it generically as Rn. Okay, so now we replace the P average with this. Next, what do? We could maybe replace the VRMS. What is the RMS of a sinusoidal? Well, we said the RMS voltage of a sinusoidal is equal to the V peak, or the amplitude, divided by square root of 2. So you put that, you square it, it becomes V peak squared divided by 2, our input. And this is what we get so far. Next, what can we do? Can we still simplify? We can still simplify. I'm just trying to kind of work it through so that we get a nice expression, and then from now on we could always use the same expression. Instead of just deriving it every single time, it becomes a hassle. And that's what we're doing here. We want to find this. We want to find what is the power that you will see here. Let's just see how it would we could develop this. So this is a logarithmic, and if you recall, when you divide inside a log, you subtract. So we could just rewrite it as such, right? We could rewrite it as such, and essentially what this is we take the 10 log 10 VP peak squared minus 2Rn plus 30, and you could actually get rid of the 2, right? So here you're multiplying, and 2 you could simply break it apart. You could have one component as 10 log 10 of 2 minus 10 log 10 of Rn, and then 10 log 10 of 2 is equal to 3, but there's a minus in front of it, so it's minus 3, so 30 minus 3, it becomes 27, and this is what you get. And this is what is the useful expression that you want. This is the useful expression that you want for the power when looking at the spectrum analyzer. So now you have everything that you need for your frequency domain representation. So this is what you see in time domain, and now you have the expression of it in frequency domain. All of it shown mathematically, right? All of it is shown mathematically. And this is very useful because, and here I wrote 2. So since all signals are formed of sinusoidal, with these equations, we are able to obtain the frequency domain of any periodic signal. So we said any signal, no matter how complex it is, as long as it is periodic, then it can be formed based on sinusoidals. Bunch of cosines and sines that you add together. Bunch of cosines and sines that you add together to get the complex periodic signal. And if that's the case, then really understanding the sinusoidal, whether sine or cosine, really understanding how it looks like in the frequency domain will enable you to represent any periodic signal, any of them. So now we are equipped to really represent any periodic signal. So this is here, what we've done here is quite powerful. And this is all done automatically by this device. But now you know how to do it analytically with formulas. Okay, so this is it. One other thing that I should mention is this is what we have in the time domain, right? Whether sine or cosine. Let's see if all these variables are also seen in the frequency domain. So number 1, we have the peak, we have the amplitude, which is V peak, and we have the amplitude. Where is the amplitude here? Well, it's here. It's here. It's in the value of the spike. The value of the spike that we see with the spectrum analyzer. So it's here. What else do we have? We have the radial frequency, omega naught. Where is omega naught here? It's here. It's the condition So basically, it's where this spike will appear. So this thing here, this value where it appears is omega naught if we're talking about radial frequencies. But usually we present it with frequency, and the same thing with an spectrum analyzer. The x-axis is frequencies, not radial frequency. So we simply divide by 2 pi, and therefore it's here. T gets replaced by F, and the phase is nowhere to be found. There is no phase, as you can see, and therefore phase has no place when we look at the magnitude of a signal. The magnitude, the frequency domain, the magnitude of the frequency domain, the frequency response, the phase is not shown. You don't see phi anywhere here, right? So it tells you that phi does not play any role when we look at the magnitude. Okay, so I hope it's all clear. And also, because you're using a device, it has an internal resistance. Well, the internal resistance is here. Now, some people, I've seen this with some people, what they do is, they do some back of the envelope estimate of what the power should be, and they assume that the internal resistance is 0. But the internal resistance it will have a contribution, right? So if you for instance, enter an internal resistance of 50 ohms, let's just do it, 50 ohms. So let's do log of 50 times 10. This is a contribution of 17 dB. So you need to subtract 17 dB. That's a lot of dBs. So I don't think it is correct to assume that the internal resistance is 0. This is a major contribution. If you assume an internal resistance of 0, the reading that you get here will not match with the analysis. So this is something that sometimes researchers fail to do, and they show us results that are totally wrong, right? This is not how it should be. So anyways, I hope that makes some sense. Now what I want to do is perhaps show you an example to see how this works, and then after that we'll wrap up the lecture. Okay, I do recognize that the lecture is getting way longer than expected, but like I promised, the next lecture will be extremely short so that we compensate for the long lecture. Okay, on to the next slide, which is an example that we will do so that we demystify this concept here of the frequency domain, which is very important for electrical and communication engineers. Okay, moving on. In this slide, I'm going to show you a numerical example of how we can determine the frequency domain. And I hope as you solve this problem, things will make more sense. And also in the assignments, there are way more problems that you could solve regarding this in the frequency series that we have. So this would be the content of assignments 1 and 2. In fact, also the knowledge that you learn here could carry forward with AM and FM signals as well. Okay, so let's see what we have. So the question is as follows. The following generated signal, right? So we have a signal, this one here, right? The following generated signal is connected to a spectrum analyzer with an RF input resistance of 70 ohms. Right, so we saw earlier we used an input resistance of 50, but in this example, let's assume the input resistance is 70. Okay, and this is your signal, right? So this is your signal. You have some information. You know it's in the time domain. So this is S of t. This is time. You are shown that for this the following wave, it's a sinusoidal. This entire duration is 3.33 nanoseconds, and it's for nano, and the amplitude is 0.05 voltage. And there's ... which means that the signal goes on forever, and also in the back as well forever. Okay, so this is your signal, and you have a bunch of questions. Question A: find the peak voltage, find the period of this signal, find the frequency of the signal, find the radial frequency of the signal. Right? So you have all this: the peak, the period, the frequency, the radial frequency. You need to find it. So just by looking at this, how do you find these values? So we'll do them together, so you get a sense of how things are done. Okay, that's the first question. Question A. Question B: express this signal in time domain. Can you write an equation for this? I gave you a picture of the signal. can you write it in the time domain? How would you write it in the time domain? Okay, so that's the second part of the question. The third part of the question is express the signal in the frequency domain. So now we want to see how to move it into the frequency domain and to express it mathematically. How do you write it in an analytical form, a mathematical notation, and assuming that we don't look at it with voltages, we look at it with dBm. So we look at big S as a function of frequency, sub P. So we're looking at the power with dBm, not in voltages. So this is what we want to see in a mathematical expression for the frequency domain. Plot the frequency domain of the signal. And when we plot the frequency domain of the signal, I tell you here, we want it as dBm versus frequency. So this is exactly how a spectrum analyzer would show it to you. And E, I ask you a question. Is this signal compatible with an RSA 306B spectrum analyzer? So it's either yes or no. And then based on that, you have to explain why this is the case. Okay, so we showed this. This is what we are using. The only difference that we're assuming that it has an internal resistance of 70, not 50. That's the only assumption. The only modification from the actual RSA 306B from Tektronix. But that's that. Okay. So you have a bunch of questions and related to this. So only this, 70, and questions. How do you solve them? Well, let's see. Let's take them one by one, and then let's solve them on the next slide. So this is an interesting question. Let's see how to tackle this question. So I just brought the figure again here, resized it in small on the corner. I'm going to rewrite each of the questions as we go and solve them. So question A, find the following metrics. If we look at this signal, what you have is you're given this. For some reason, you're given this. And you're told that this entire duration is 3.33 nanoseconds. Now, you could also inspect it and then see that the period is repeated a couple of times, right? There's a pattern, and the pattern is repeated a couple of times. In fact, you could inspect it and count it. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. So the pattern is actually repeated 8 times. But when we want to find, for instance, the period, we don't want 8 times. We just want one of them. So that's how you would find it, by simply inspecting this. As for the frequency, it is simply 1 over the period. So once you have a period, you can right away find the frequency. You just do 1 over. And as for the radial frequency, you simply multiply by 2 pi. Whatever you got here for the frequency in hertz, you multiply by 2 pi, and you express it in rads per second. And for the peak voltage, well, it's here, right? It's here. This is the peak voltage, 0.05 volts. So we have everything by simply inspecting it. So I'll just show it to you. This is what we get, okay? So as we said, the peak voltage is 0.05. It's here. It's also minus 0.05. The period is this entire thing, 3.33 nano. Nano is 10 times 10 to the minus 9. I hope you know your engineering notation. This is back to electrical fundamentals. You've probably taken this course with me the first semester. And we said there are 8 of these cycles. So you divide by 8 because we're not interested by 8. We're only interested by 1. And we end up getting 0.416 nanoseconds. So the period is this. This is the period. Okay. The frequency is simply 1 over the period. And so you do 1 over 0.416 n for nano. And when you have a nano in the bottom, when you flip it, it becomes 10 to the 9. And 10 to the 9 is giga. And therefore, we write gigahertz. And 1 over 0.416 is about 2.40. So that's 2.40 gigahertz. The radio frequency, it's simply 2 pi f naught. So you have your 2 pi and you have your f naught. F naught is 2.4 times 10 to the 9, right? It's just giga, so 10 to the 9. You multiply with a calculator and you get this. You get 1.51, roughly. I put roughly. It's about 1.508 but you round it. So don't forget, with my evaluations, if you do evaluations or quizzes and all that, always make sure that you stay to 3 significant digits. So don't go beyond that. In labs, you could use 4 significant digits. In handwritten and in work that you do during evaluation, 3 significant digits. And don't forget to always also use engineering notation. In this case, I did not use engineering notation because I'll show you why in a second, because we have to express it in the expression for the signal. But we got 1.51, 3 significant digits, times 10 to the 10 radians per second. So now we have all the 4 items that we want. And we got all this by simply inspecting the visual of a signal. So you should be comfortable going from this to a picture, or going from a picture to these values. So this is how one would read a signal, a sinusoidal signal. Okay, and you could do the same thing with other type of periodic signals if need be as well. Let's continue. So B, express this signal in time domain. How do we write this signal? Now with a formula in time domain. So we could just show it to you here, and basically S, this is called S, so we just write S. And the equation for a sinusoidal is always VP sine omega naught t plus phi, or if you want VP cosine omega naught t plus phi. And we said they're both similar. There's only the phase that changes. So in reality, you could always present it as a sine. And in fact, if you inspect this, once it begins like this and it goes up, it begins at the origin here and it goes up and it comes down. This is 100% a sine function, and it has no phase. So the phase is actually 0 here. So you could just plug in 0 for the phase. So that's gone. Omega naught, you found it here. So 1.51 times 10 to the 10. So you could just rewrite it here. And then you have your t. You just multiply by t. And your VP, you already found it. It's your amplitude. It's 0.05. So this is the equation to get this. So if you use, I don't know, some tools like Mathematica or MATLAB or any other different plotting tools that exist, you could simply enter this function and you would essentially get such a figure. So we answered B as well. Let's move on to the next one. C is in the question, it says express the signal in frequency domain. Express the signal in frequency domain. So we basically want a formula. We want a formula, a mathematical notation for this signal in the frequency domain. So the most important thing in doing so is to determine what is the power of the signal. Once we know the power of the signal, then we could write the expression. So let's just write the expression. So we got this part from what we derived in the last slide. So I showed you how to derive this. So we already derived it. It makes our life much easier. We just rewrite it, 20 log 10. And instead of VP, we just enter the value. So that's 0.05 minus 10 log 10. And the internal resistance of the spectrum analyzer. In this example, we said the 70. So you enter 70. And then you add plus 27. So this comes straight from what we just derived earlier. And now you just use your calculator. So you do the log, you get minus 26 for this part, 0.0. You do the multiplication here, you get minus 18.5 for this part, and then you have your 27. You add everything together, you get minus 17.5 dBm. So that gives you the value of the power. So basically the power of your signal. You determined the power of the signal. Okay. And you express the power of the signal in dBm. And like we said, we're interested by this because spectrum analyzers, they always show it in dBm. Okay, so in reality, dBm is just a convention that electrical engineers write. But if you want to be more precise, it should be dBmW, right? It's a watt. It's watts, but milliwatts, and you're expressing it in dB. But nobody does that. All the devices, all the electrical engineers around the world, they just write dBm. Okay, and so we just live with what most people do. Although, if you ask me, it's not very accurate. But let's move on. So then, now that you have this, you could pretty much, just write the expression for the frequency domain of the signal. So basically, you would write big S, P for power. It's a function of frequency. That's why you have F. You have absolute value because this is a magnitude, not absolute value, but this is a magnitude. So absolute value is a special case of a magnitude operator, but nonetheless, so you have this, and you just basically write the value of the power, so it's minus 17.5 dBm, and this is only shows up as a spike for the frequency of 2.4 gigahertz, okay? And everywhere else for all other type of frequencies, 1 gigahertz, 1.5 gigahertz, 1.2 gigahertz, whatever it is, all the other frequencies, you get 0. Okay, so that's kind of a model or a mathematical notation of how your spectrum analyzer is. So now we move on to the next question. The next question says, now that you have an expression of your signal in the frequency domain, can you plot it? Can you plot this graphically? Plot the frequency domain of the signal graphically, and let's see how it is. So we do it, and this is what we get, right? So it's just a spike at 2.4 gigahertz. So this is a frequency domain. On the x-axis, you have your frequency. On the y-axis, you have your value for the power in dBm. And you look for where is this? This is located at frequency equals to 2.4. So the frequency here is 2.4 gigahertz. And it's a spike. So it's just a line, if you will. And the height of this line is at minus 17.5 dBm. Okay, so that's basically what it means. Okay, so this is what we get. By the way, if you get a minus dBm, let's say, I don't know, you get minus 25 dBm, it will be shorter. So smaller power, it will be shorter. If you get, I don't know, 1 dBm will be longer. So you have to be careful of how to read this. So if you have a value that is smaller than this, well, it will be smaller, right? So if you have a value like, let's say, minus 30 dBm, minus 30 dBm is not bigger. It's a smaller line, but if you have, let's say, I don't know, minus 5 dBm, minus 5 dBm is bigger. So it's bigger. It's like the temperature. Temperature, when you look at degrees Celsius, minus 5 degrees Celsius is hotter than minus 40 degrees Celsius. That's kind of the same thing here. So you have to be careful of how to do that. Now, this is how we represent the result of this signal in the frequency domain. But if you use your spectrum analyzer, you're not going to see just one thin looking spike. You might see something like this, right? So you might see, you know, so like a curved. Some might say it looks like a bell-shaped figure. Now this is kind of extreme. It's a GIF file, so it's also moving fast. I got it from Wikipedia. So you might see some different shape of it, but it doesn't go all the way to infinity. It has a certain height. The height will be the value of the power, but it's not just one spike. It looks like a bell shape. Okay, so just be mindful that your spectrum analyzer will not necessarily show something very, very thin like this. It will have some bell shape to it, but the bell shape will be quite thin. The width of it will be quite thin, not thin almost equal to 0 where it shoots up to infinity. That's not what you will see. We're in real life, but that, just so you know, this essentially is a model of what one would see in real life, right? But quite accurate model nonetheless. Okay, so let's move on to the last question. So is this signal compatible with the RSA 306B from Tektronix? And what do you think? The answer, perhaps you will get it. The answer is yes, it is compatible. The reason why it's compatible is that if you look at the data sheet for the spectrum analyzer, the Tektronix spectrum analyzer, the one that we are using that we connect with the USB, it said we noticed that the frequency range is from 9 kilohertz to 6.2 gigahertz. Well, and I think I told you that before. And the power range of the spectrum analyzer is anywhere from 20 dBm to minus 160 dBm. So here we have everything. We are the signal frequency is 2.4 gigahertz, 2.4 gigahertz is within this, so check, this is good. The power value is minus 17.5. Minus 17.5 is within 20 dBm to minus 160 dBm. So that's also check, that's good. Now this is an example that I gave you, and in reality this example kind of resembles what a good signal for Wi-Fi, right? 2.4 gigahertz is what you would essentially see with Wi-Fi. Wi-Fi, we said it has two possibilities, 2.4 and 5 gigahertz, and having a power of minus 17.5 dBm is not bad. It's actually a relatively okay signal quality for Wi-Fi. So that's not bad. It means that you are relatively close to the access point or the router, the wireless router that is giving you the signal. So that's good. So well, we talk more about these things in the wireless course, but nonetheless, I just wanted to kind of show you that these numbers are not just some numbers that I picked up randomly. They have some significance, and they are in fact compatible with what you would typically see with Wi-Fi connectivity. So that's it for now. This is this lecture essentially is a long lecture. It's a lecture for both lecture 2 and lecture 3 combined together. And in the next lecture, what I will do, so lecture 4, we will talk about filters. We will talk about upconversion, and we'll introduce to you AM and FM. Now, like I said before, we are losing 1 week in this semester, so there is that, but nonetheless, we are trying to show you as much as possible. So we'll see how much we can advance with AM and FM. If we don't advance too much, let's say with FM, if we don't have enough time, that's okay. As long as you see some of the key ideas, then that's important. So what I showed you here are all things that are 100% relevant even today. So it's not just analog. These are useful stuff that you could use certainly in signal processing and also in digital communication, and that's why I found it important to spend time on it. And I created this comprehensive video for you so that you study it all in one shot, and that's it. So thank you for your attention, and just just keep monitoring your slate for recent updates. Thank you so much, and have a good day.